Hello everyone. My name is Marco Santoni, and I'm going to talk about how to apply Bayesian inference with PyMC. So imagine we work for an e-commerce company, and we are redesigning the website, and the IT guy comes and say, okay, we have to decide either to use a blue button or a green button. So our boss say, okay, which is the color that sells more? So we want to set up an experiment and evaluate what's the probability that one is better than the other, basically. So it's a classic A/B test. So we set up the experiment. When a new user comes, we either send him to page A or to page B. And then we can count whether he bought, for example, a teapot or not. So the most basic approach is just to compute the average. So we count how many times he bought over the number of times that over the number of users that visited the page. So, but there are some limitations with just computing the average. So we can raise like, what if n is small? Are we still confident about the result? Or what is the number of users that we need in order to have 90% confidence in the result? Or what if n is different for page A and page B? So we have 1,000 people on the first page and just 500 on the second one. How can we still be confident about the result? So today I'm going to talk about Bayesian inference to answer this question, basically. So there are two main interpretations of probabilities. One is the frequentist one, and the other one is Bayesian. For the frequentists, they see probabilities in terms of frequency. So for example, we observe 4 car accidents out of 1,000, so the probability of a car accident is 0.4%. But this has some limitations. So it cannot be applied to all cases. For example, if there is some elections, and then what's the probability of a politician winning? Here it's a bit harder to think in terms of frequency. For the Bayesian interpretation of probability is rather in terms of belief. So how much do we believe in some event, or how much are we confident in the event? So the claim is that the way of interpreting probability as a Bayesian is a more natural approach. So it's useful to be able to produce some results that are easy to interpret and to represent. So let's look why. So imagine we are writing some code, and we want to write some specs to test whether the code is running or not. So we write the first set of specs of tests, and the tests are successful. So we decide to run a second experiment with more tests, more complex ones, and the tests are passing again. Then we run a third set of tests, and the tests are still successful. So our confidence in the fact that there are no bugs is increasing more and more. So this is similar to the way a Bayesian thinks. Like the workflow is usually that we have some prior belief about something. So we are confident, like 50% that the code is correct. Then we observe new evidence. So tests are successful. And then we update the belief based on the observation. So if we resemble this as a developer point of view, we have a statistical problem. And if we represent a frequentist view like a function, it would just return 80%, for example. So just the frequency of some event. For a Bayesian, a function would return something a bit more complex, that is a density function. So for example, we are confident that the tests are passing with an average of 80% of confidence, but in the range of, I don't know, 50, 90. Or maybe we can express less confidence and say we don't know anything, so it can be anywhere between 0 and 100%. So the question is, how do we compute this thing here? So we can use the math, and starting from Bayes' theorem, which probably most of you know, and which works well for examples, so to compute the exact form solution. But for realistic case, it can be hard to find the closed formula to represent any kind of problem, or realistic cases where we have more variables and it's hard to solve analytically and find a solution. So I'm going to talk about PyMC, which is a Python library to perform Bayesian inference. And the idea is that MC stands for Markov chain Monte Carlo, one of the two, and which is a numerical approximation of Bayesian inference. So instead of having a closed form solution of a density function, we have a numerical approximation of it. It's also known as probabilistic programming. So let's look at an example. So we are back to the A/B test. And so we have two web pages with two different colors, blue and green. And there is just one difference between the two, because we have to make sure that the cause of the different buying rate is due to this single cause. So we set up the experiment and forward the users either to page A and page B. And so we assume that there is a PA variable that represents the probability of clicking buy when landing on page A, and PB, the probability of clicking buy when landing on page B. So we want to investigate which one is better, so which is finally the page that we want to choose. Yeah, so how do we compute PA and PB in terms of density functions? So we set up the experiments, and we have NA visitors and CA number of clicking buy on page A, and the same for page B. So like the solution for the frequencies would be, again, just compute the rate, basically. But the observed frequencies does not necessarily equal PA, because maybe we have just few examples, and then it's hard. It's not likely that always this frequency is exactly PA. So we try to set up the Bayesian experiments and infer the true frequency from the observed data. So now we first look at some code just for one page, and then we extend the example for 2 pages. So usually the workflow is quite simple. It's made of 3 steps. First, we define our prior belief about the event of the random variables. Then we fit this prior belief to the data and to the observations. And then we get some posterior distribution after the observation of the data. And this is where we are going to do the inference and get the results. OK, so first we just generate the data set. So we set the true probability of buying something to 5% and on page A, and there are 1,500 people. And then here, this is just a function that is sampling a coin 1,500 times. And the result is an array of ones where basically the object was, the clicking buy was done. So this is just an array, so we can see, OK, how many times it was clicked. And in this case, there were 68 clicks. And the observed frequency is 4.5%. So quite close to the true, but not exactly the same. So now we have to define our prior. So we model the clicking by event like a Bernoulli distribution. So the probability of clicking is equal to P. And so the probability of clicking is equal to P, and of not clicking, 1 minus P. So the goal is to understand what's the value of P, which we call PA as well. So now we define the prior. So we have this uniform class of PyMC, which we give a name of the variable. This can be foo bar, or we can give a meaningful name like PA. And here we define, so basically we chose to use a uniform distribution between 0 and 1. Basically we are saying we have no subject prior belief about where exactly PA is, and so we are a bit conservative. Otherwise, if we have some extra information, we can use some different functions to say, OK, maybe I know that the value will be likely here. But in this case, let's just be conservative and use a uniform distribution. So basically, what we have done here is to define a random variable. So it's a class. So it's not a real value. It's just a random variable. So we can sample it, and then with this random method, and just we'll take a value out of it, which is stored, and then if we sample again, the value changes. OK, so we then define the prior of the click event, which, as I said before, is a Bernoulli random variable. So in PyMC, we use again, OK, we give a name, obs, because we are fitting all the observation to it. And PA is the parameter that controls the Bernoulli variable. So in this case, we don't set a value because we don't know what's the PA. And we set our prior random variable that we defined before. And then we use these two arguments here, which basically we are saying, not like before, we had here the value which is changing each time you sample. But basically we are saying, OK, these are the values of this variable, and observed equal true, so they are fixed and do not change them. So here we have done the prior. We have defined our prior belief about the experiment, and now we fit this prior belief to the data. So here we have a magic box, black box MCMC. So we are defining the model, and we pass a list of the variables. Here the order doesn't matter. And then here the sample method is where the model is being fit. So here, just qualitatively, what's happening is that the prior belief are being updated with the data, and it's computing the posterior belief. So I will skip now the description of this part here, consider it like a magic black box. I will detail it a bit later. So the result of this is that this object has a trace, which is the numerical approximation of the distribution, of the posterior distribution. So for each variable that we define here, we can access it with the same name, and it will be just an array of values, which we can see as an approximation of the posterior distribution. So the result of the fitting is basically a set of arrays. So we can plot the histogram of what has happened so far. So here we have the true value of the probability of clicking by which generated the data set. And here is the numerical approximation of the posterior distribution. So we see that it's quite close, and we have some confidence, which is why we set up this Bayesian inference, because we want not just to say, okay, our estimate is 0.45, but it's a probability density function. So we can say, okay, we are confident that the true value of PA is somewhere here. So we can also answer this kind of question. We want to have a confidence of 90%. What are the confidence bounds so that we can say P is between these values with 90% confidence? And now it's very straightforward to do, because we have this trace here, which is just an array of realization of these random variables. And so the size of the array is something that we defined before as this sample size of the numerical approximation. And the lower bound and the upper bound we just compute as the 5 percentile and 95 percentile. And then we can compute, okay, in this case we have, there is 90% probability that PA is between 3.7% and 5.4%. So it's a nice way to have this kind of clean statement, very easy to read and to understand. So what if the number of users on page A is lower? How does it change the experiment? So let's say the same as before. We have same probability, but we only have 50 people. So we do the sampling part. And in this case, 2 people clicked. So the observed frequency is 4%. Close, but not exactly. But can we really be confident about this result? Because we just have 50 people, so maybe it's not so reliable. So we run exactly the same as before. Prior, then fitting of the model. Here, 20,000 is the size of the final array. And then the histogram now looks a bit more flatter. So basically, okay, the mean of the posterior distribution is somewhere here, but our confidence is, I don't know, between 0 and 10%. So we can express the same result as before and get a different result. So there is 90% probability that PA is between 1.6% and 11%. So it's a nice tool to make this kind of assessment without having to do like crazy math. And we can also go to the business and say, hey guys, here you have 90% of chance that the true value is somewhere here. So here I just put one along the other on the same scale, and you see the difference between 1,500 times of people in the experiment and just 50. You see how the confidence jumps up. So now let's look at the full experiment with 2 pages. And the question is, does the red have a larger probability of being clicked? Sorry, blue. This is a mistake. OK, so this is similar to before. Now we generate the data set. We say the true PB probability is 4%. And to make it a bit more realistic, we assume there are different number of people on page A and page B. In particular, on page B, just half of the people. And so we do the sampling. And here we observe a frequency of 5.3% and 4.1%. So we define PA and PB as uniform priors, as before. And then we define an extra variable, which is delta. So here we use a wrapper, which is from PyMC, which is the deterministic wrapper. And what is done is saying, okay, now we are defining a random variable, which is random just because it depends on other random variables, but it's a deterministic function of them. So once you have a value set for them, then it's a dependency deterministic out of them. So it's basically a third random variable of the model. We can see it as a child variable of the two, if we see it as a graph. So we define again the Bernoulli prior of the observations as before. And then here we define the model again with all the variables of the model, which are a bit more, and the size of the simulation. So now we have three posterior distribution, PA, PB, and delta samples. So we have these three arrays of realizations of the simulations. So now we can do some more histograms. So let's look at the histograms of PA, PB, and true delta. So here we see that, okay, more or less it's correct. So the histogram is around the true value here and also here. And we see also that PB, since there are half of people there, it's a bit flatter. Here the top is around 60% and here 70 or 80%. So this distribution is a bit flatter than the other one. So we are a bit less confident about the probability of clicking on page B than we are on page A. And then this is the posterior of the delta. So basically it's the difference between PA and PB. So it's above 0 most of the times. So we have quite some good confidence that PA is better than than PB. So let's quantify these numbers. So like the question is PA greater than B? And if so, how much are we confident? So we can compute very easily the probability that PA is greater than PB by just taking the posterior distribution of the delta and count when it's greater than 0. And then just do the average, the mean. So in this case, we have 89% probability that PA is greater than B. So it is very easy to get these results, which are easy to explain and to express and to show to your colleagues. So now we have looked at this size of the data. Let's look at a bit more unbalanced example. So let's say that on page B there are even fewer people, just 200. So how does the result changes? So here we set the two one next to the other, and yeah. So basically here we see that the posterior of B is much flatter than before because we just have 200 people, so we are way less confident about your result on page B. And as a consequence, since you're less confident on page B, also the difference is flatter than before. And then we compute again what was before like 89%. Now the probability that PA is greater than B is just 73%. So yeah, this is one example end-to-end how you can compute these results quite easily, and then you can play around with the posteriors very easily, and it's nice that you have clean results. So now we do a very quick look about MC, so Monte Carlo Markov chain. So this is something that we have seen before, and now let's look at what this means. So basically, we have the priors of the probabilities, and the goal of this part is to compute the posteriors. So the posterior of PA, PB, delta, given the observations. So as I said before, we are not having a closed formula for them, but we have numerical approximation. So basically, these posteriors is just represented by samples. So the goal is really to, how do we create these samples? So Monte Carlo Markov chain is a family of algorithms, and by default, PyMC, in the example that I've shown, is using what is called Metropolis Hastings algorithm, but there are also different ones which you can choose when you define the model. And these two parameters are the number of iterations and the burn-in. So now I will explain what this means. So the iterations is basically how many samples you want to simulate. So the bigger the number here, the idea is that the bigger the number, the smoother and the more reliable result you have. But it's also computationally more expensive. And the burn-in period is, so basically what's happening here is that the algorithm is trying different values of this. Each sample is a combination of different values of the variables. And each time you try a new value and you decide on some criterion whether to keep it or not. So the idea is that the first samples are a bit more exploration phase. So you can get to some areas that are not so reliable. So this is saying, okay, we run 25,000 simulations, but we discard the first 5,000 because it's just an exploration phase. So at the end, we have 20,000 samples. So the higher the burn-in, the more samples you discard at the beginning, but then the less samples you have at the end. So I will not go inside the details of the Metropolis hasting algorithm because I think it's quite complex and out of scope. But yeah. So yeah, PyMC has some nice tools to get an idea of what's going on inside the black box. So let's open the black box. We have this plot called MC plot, which basically shows what's going on inside the algorithm. So this is the result that we have seen before. And this is a trace of the samples that were basically computed during the execution of the algorithm. So this is an index of the number of the samples. So the first sample was here, and we see what is the value of the samples over the running of the algorithm. So the algorithm is running from here to here, and each time you see which samples were tried out and accepted. And you can, the idea is that with this plot, you can see whether the algorithm is converging or not. Here it's, I mean, you see the sample is quite flat, but maybe here you have a wave like this, and then you say, okay, it's not converging, so either something is wrong with the model or the parameters, or I need more samples. And this is the autocorrelation plot, which the idea very quickly is that the lowest the autocorrelation, the more likely you have converged. Now, basically here, the higher the autocorrelation, the less likely you have converged. So these are tools to understand whether the algorithm has converged or not, which are for free inside the PyMC library. So this is the same for PB and delta. So in conclusion, PyMC allows to easily interpret Bayesian inference. You can express confidence very easily without p-values, which are not always easy to explain to your colleagues or business, maybe harder to interpret. You don't have to do any crazy math, and it can be computationally expensive. But the idea is that also this is quite suitable when you have little data, and so you really have to think about the confidence. Because if you have large data, then just the mean or the frequency works, because for the law of the large numbers, basically approximates the true value. So when you have little data, which is quite often, it's a nice tool, basically. So this is a book that I read to learn about these tools. I really recommend. It's called Bayesian Methods for Hackers by Cameron David Pylon. And yeah, thank you for the attention.